Okay, so, you know, we also have this, I don't think I did that on camera, but it's, you multiply F parallel by your displacement, right? Meaning if you're moving in one dimension along a straight line, you choose a positive direction. And if the force is not on that line, you take the component of the force that is. And that will either be positive or negative depending on which direction you chose as positive. I keep emphasizing that. And your displacement. If your force is like this and your displacement is back here, then one of them is going to be positive, one of them is going to be negative, whichever direction you choose to be positive. Okay, then in the ideal case, in this case, then we'll at first regard the rubber band as ideal, right? So we can. We're going to find out that it isn't, because if it was ideal, the rubber band would have gone a lot further. Okay? But once we figure out how far the rubber band goes in the ideal case, we're going to have some basis for saying that there are non-conservative components to the forces here, right? Now you might have trouble distinguishing those from what happens because of air resistance, because that's also significant. But I didn't include that. We're just getting an estimate here, okay? So you kind of say, okay, I'm going to ignore air resistance even though I know I can't. But if air resistance isn't a big deal here, then I'm going to get a good result, okay? I know I won't because it is, but we're going to assume it isn't. Make sense? Okay, well, hopefully. And if all that sounds like a bunch of gobbledygook, listen to it again, it'll sound even worse. Okay, so we have this, and we're going to make this assumption, even though it's not really true for a rubber band, it's not a bad first approximation. Okay? And in Lab Friday, we're going to deal with rubber bands and some other things. Okay. Okay, anything else?